Hi folks, here really my name's James and I'm here to talk about sine waves and trigonometry, and it's a lot of the stuff that I usually teach, and there's a lot of questions people usually ask about it. So we'll just start off the definition of a radian. For any circle, if you've got a radius, the red bit there, and then you draw a circle and then you lay the length of that radius around the outside of the circle like so, then the angle between the two ends is 1 radian, which is roughly 57 degrees. So then, as you can see in a circle, in just under half a circle is 3 radians, half a circle is just over 3, which is pi, and so for the whole circle, and this is true of every circle, it has 2 pi radians, which is about 6.3, and that's true for every single circle. We'll just go over that once more. Take your radius, no matter how big your circle is, draw your circle with that radius, then take the length of that radius and wrap it closely around the outside of the circle, and then the angle between the two ends is 1 radian. So that says it all really. 3 radians, just under half a circle. Pi radians is the same as 180 degrees, and therefore one circle which has 360 degrees is 2 pi in radians. Because I do a lot of electronics and maths, sine waves and things like that often pop up with voltages changing over time, and the fundamental equation for a sine wave has this little term in it, omega, and that's the angular frequency, and maybe we can explain what that means. Omega is, say, the number of circles times the angle in a circle per second, or if you imagine your sine wave spinning as if it's a little ball on the end of a string and you're spinning the ball in a circle, however many times it completes one circle in per second is the angular frequency. But the angle in a circle is 2 pi in radians. So omega is the number of circles spun per second times that angle, which is 2 pi. So the angular frequency is angle per second, or radians per second. And this is the term that I use that probably no one else does, but you never know. Radian hertz, because really omega, the angular frequency, is how many radians your sine wave or cos wave goes through per second. And maybe we'll get there's a fantastic graphing tool called Desmos. It's a brilliant graphing calculator. And here I've got a sine wave, and I mentioned about that equation for sine waves, very similar to the one for cos waves. The fundamental sort of equation, as I see it, is the y value, the value of the y-axis for any value along the x-axis. So there's our x variable, the independent, and here's our dependent y. It's like the output. The value of y is equal to a times the sine of omega x. And what you'll often find is, or most of the time, sine and cos waves, we're measuring their value with respect to time. So usually the x-axis, or the x value, is time, and the standard unit of that is seconds, even though it may be micro or milliseconds or even smaller. The standard unit is still seconds, so we have to use engineering form. Like if it's a millisecond, we'd have to put 1 times 10 to the minus 3. But don't worry too much about that right now. So y equals a sine omega t is when we've got time on our x-axis. And here we can explain, the whole point of this video is really to explain what some of the sort of attributes of a sine wave mean, some of the variables. And like we said earlier, omega is the angular frequency, and it's equal to 2 pi f. Omega is equal to 2 pi times the frequency of the sine wave. So if the sine wave span around, as it were, once per second, then 1 per second is a frequency of 1 hertz. So 2 pi f is omega, and if f is 1, then omega must be 2 pi for that equation to stand true. So let's have a little look at this, how things change as we move different sliders. So we've got A is known as the amplitude. It's also known in electronics as the peak value. It's the distance from 0 to the maximum. So here our A, our amplitude, is 1. That's like 100% of what the sine wave can ever get to. It can never get bigger than the amplitude. So whatever you've set that to, whether it's volts or meters or anything, that's the maximum it will ever get to. And you know that the other extreme, the negative peak, is the same value, but it's the negative sign. So the distance from here to here is minus the amplitude, or minus A. And as you see, if we take this slider and we increase the amplitude, all we're really doing is making the sine wave taller. We're not changing its frequency in any way, we're just making it taller. And if we make the amplitude 0, then 0 times something is 0. So A, if A is 0, A sine something is 0 anyway, regardless of any other variable. Then if we bring A negative, we've still got a sine wave, but it's upside down, if you like. It starts going negative first, because the amplitude, as this equation sees it, A is negative, so it's just an upside down sine wave. But the most common ones, well, that I find, are where you've got a positive amplitude. That's your fundamental sine wave, if you like. So that's what happens as the amplitude changes. From the equation y equals a sine 2 pi f x, or 2 pi f times t, where 2 pi f is omega, and omega is always 2 pi times the frequency of the sine wave. That's always true. If we increase the frequency, basically if something's more frequent, more of them happen per unit time, and a unit of time is a second. So if something's more frequency, if the frequency increases, it's more frequent, so you get more of them per second. And as I've got on my x-axis here, time, I didn't put it, I should have really, is in seconds. And here's 1 second. And as f goes up, we get a lot more cycles per second. And we know exactly how many. When the frequency is equal to 1 hertz, that means 1 cycle per second, because that's what hertz means. So when the frequency is 1 hertz, we have 1 positive peak and a negative peak, and back to 0 in 1 second. And of course, you may or you may not know, but the period of this waveform is the time taken for it to go from 0, positive, through 0 again, negative, and back to 0. That is 1 wavelength, or 1 period, or the length of time it takes for 1 little sine wave to happen. And the period is 1 divided by the frequency, which makes sense really, because if it takes you, say, a certain amount of time to do something, then say you go shopping and it takes you half a day to go shopping. And if you're always shopping, by the way, that would mean that you do it twice a day. So if it takes you half a day, is the half, 1/2 is the period, then the frequency at which you can do it is 1 over that. 1 over a half is 2. So they are like inverse of each other. As the frequency increases, more sine waves fit in per second. And Desmos is really good for showing this. If we take the equation and we add something called a phase shift, You can see this equation written here in loads of different ways. Sometimes they're put in a different way to confuse you, but if you see it in this sort of form, it's always a sine wave. The sine is a bit of a clue, but the value of y at any given time is equal to the amplitude times the sine of omega times the x-axis, which is usually omega t. And sometimes you'll see plus or minus a little angle, and that angle can be theta or alpha or anything, depending on what people have chosen to call it at that time. I'm putting a little p, pardon me, a little p in for phase. So what the phase difference is, it's if you've got a positive phase difference, it means that compared to a standard sine wave that starts at 0, if we increase the phase, look what happens. Look, it's as though this sine wave, the orange one that's phase shifted, has happened. It started happening before. So by the time we get to 0 time, it's already at its peak. So a positive phase shift, as in when this angle here, which is usually theta, but I put it as a p for phase. When this is a positive, it means that the sine wave has happened a little ahead of time, which means it's leading a normal sine wave. And what I mean by a normal sine wave is one that starts at time equals 0 and goes positive first. So as we increase the phase difference, it will go up and up and up and up out of phase. But if we take the phase as being negative with respect to what I call a normal sine wave, then negative means it's happening after, it's starting later, because this is where it starts, and time has happened between there and there, so it's happening later. So it's said to be lagging. If something's lagging, it's happening later. And this is getting more laggy, more laggy. But what you'll notice is, if the phase difference is one whole cycle, as in 2 pi radians or 360 degrees, then it's back in phase again, and nobody would know any different. So if your phase shift is minus a whole cycle, or plus one whole cycle, as in 2 pi radians or 360 degrees, then it's actually back in phase. So technically there's no phase shift. So that is periodic in 2 pi, in the same way that the sine wave is periodic in 360 degrees. That just means that it keeps repeating itself. In the same way that, like, say, your minute hand on your watch points in the same direction once every hour. So the minute hand is periodic in your hour, and your hour hand points the same way every 12 hours. So that's phase. Just remember that positive phase, as in a positive angle here, means it started previously to a normal sine wave, so it's already started happening. A negative phase shift means it's happening afterwards, so it's lagging. That's leading, that's in phase, and that's lagging. But if you lead or lag by 360 degrees or 2 pi radians, then the phase shift doesn't really exist. You wouldn't even know. So it's the same as if there's no phase shift at all. Now there's another part of the equation. Y equals, obviously the fundamental again, y equals a sine omega t, or y equals a sine 2 pi ft, because omega is always 2 pi f. And then we've included a phase shift, but at the moment I've set the phase shift to 0. But then there's something else, another number that we're adding on the end. If you think the equation y equals mx plus c, the equation of a straight line, then the c is kind of like the intercept or the offset. And this is very similar to this. I've called it DC, and that's because I'm an electronics engineer. And we often refer to this as a DC offset. It's the amount that you shift your sine wave up or down. Imagine that when it's symmetrical around y equals 0 around the x-axis, then that's like jumping on a trampoline up and down, whilst you're on the ground level. But then if you increase an offset, as in you're adding a number to the overall value of y, this is your normal y value, but then you add a little bit to it. Let's see, as we increase the DC, all that's happening is it's adding that number to the value that the sine wave's already at, and it's offsetting it. If I zoom out a tiny bit here, what we'll see, increase the DC offset to 2, and where the sine wave normally starts at 0, now it's starting at 2. So that's like jumping up and down on your trampoline on the second floor of a building. Remove the DC offset, set it to 0, and you're back where you were. You can go negative though. You can take away a positive or add a negative. It's the same thing. If the DC offset is negative, then that's like jumping on your trampoline in the basement 2 floors down. So really, that's all it is. So you shouldn't be put off by any of these equations really. Y equals a sine omega t. It's omega x, but we often put time on the x axis. Omega is equal to 2 pi times f, which is the angular frequency, omega is, in radians per second. And the frequency of the wave is in hertz. And the next thing just to go over is the relationship, I suppose, between omega and f. So let's let's put a sine omega t, or a sine omega x, where x is time. Let's increase omega. At the moment it's 2 pi roughly. Pi is about 3.141 or 22 over 7. So this is 44 over 7, which is 6.28 something. It's 2 pi in radians. Because omega is 2 pi f, and here we've got omega is 2 pi, that means the frequency must be 2 pi over 2 pi, because if omega is equal to 2 pi, but it's also equal to 2 pi f must be 1. So the frequency is 1, so therefore 1 over 1, the period, 1 over f is still 1. So this kind of proves that when your frequency is 1 hertz, your period from there to there is 1 second, and your angular frequency, omega, is 2 pi radians per second. Now if we increase, let's stick 2 graphs on here. One of them's in terms of omega and one of them is in terms of f. I've just got different sliders to change different variables. So let's decrease omega down to about pi. So the black one here, the black sine wave, I'm going to try and make it so the angular frequency is about pi. There we go, that's pretty good. So the black one has an angular frequency of pi radians per second. And if omega, remember the equation, let's go back to this, omega is equal to 2 pi f. If omega is equal to pi and omega is on the top, then what's f going to be? Pi divided by 2 pi must be a half. So let's just check, is that right? We want to make these two sine waves match up. So let's try making the frequency a half. See if they match up. Yeah, excellent, fantastic. Sort of wipes his forehead, thinking, goodness, I'm glad that happened. So we can do this the other way around. Let's say that our frequency in hertz is 2 hertz. This is the blue one that we're moving now. So to make it a bit more clear, let's turn that one off. The frequency is 2 hertz, which means that we've got one cycle and another cycle, 2 cycles in a second. So the period is half a second because it's 1 over 2. And so going back to this equation, if f is 2, how do we get 2 from something divided by 2 pi? And what's that going to be? Well, let's change omega and see what value it has when it reaches and matches this. Can we do it? We can't do it here because we need, if this is going to be 2 and on the denominator is 2 pi, then that has to be 4 pi. So let's change this slider here to see if we can change omega to step up to, I don't know, 13, something like that. So when the frequency is 2, let's get them to match up. There you go, that's 4 pi. So it all adds up, which is reassuring really. So hopefully this may have taught you a little bit, or reminded you. Trigonometry can be a little bit confusing sometimes, but all this really is the equation of a sine wave, where the y value at any given time, time's usually on the x-axis, so it's actually called x here. The y value at any given time is equal to the maximum value, the amplitude, which is called the amplitude, or the peak voltage or peak value, times the sine of omega t. And omega is 2 pi f. And then, just to get nasty, sometimes we include a phase difference. A positive phase difference with respect to a normal sine wave. A positive phase difference means it's happening before, it's leading, or a negative phase difference means it's happening afterwards or lagging. In addition to this, we could have a DC offset, which is just like adding a number to what y would have been. So it's a shift up or down basically. There you go, that's shifted up, that's shifted down, and this is where the offset is 0. And of course what you can do with Desmos is fantastic calculator. If you're inclined, you can change the amplitude, you can change the phase, change the DC offset, and you can impress your friends, I'm sure, at parties. So yeah, my name's James Cleves, and thanks so much for watching, and any questions, just leave a comment. Cheers.